Alright, so we'll go over basic introduction to integration under calculus. So what is integration? So you can think of integration as the opposite of differentiation. In other terms, we can call it anti-differentiation. So when you hear the word antiderivative, don't basically be confused. Just know that it's the opposite of basically what you do. So under differentiation, we already know that if you have a function, for example, y is equal to 2x to the power 3, you understand that, of course, let me add the 1 there. You understand that if you try to determine the derivative of this function, it is going to be equal to 3 times 3 times 2, 6, and then x squared. So, of course, the constant goes away. So, this is differentiation. Now, the opposite, where you need to reverse that back to that is what we call integration. So, basically, we know that according to power rule, if you're trying to determine the dy dx, which is of course the derivative, what we said is when you look at 2x to the power 3, what is going to happen is you're going to subtract a 1 from the power. So from the 3 reduce a 1, and then of course I think the first thing before I actually lose you is when you look at the 2x to the power 3, first thing is multiply 3 times 2. Okay, so you multiply the 3 by the 2 and then reduce the power by 1. So if you multiply 3 times 2 I have 6 and then reduce the power by 1, that is 3 minus 1, and then that is your answer. The constant disappears away. Okay, in other terms, if you look at the constant plus 1, it's more like what you have is 1 multiplied by x to the power 0. 0 times 1 will give us a 0. So that's why constants disappear. Okay, so of course this becomes 6x squared. Now if you're trying to think of the opposite, what you might expect is we'll do actually the opposite. So the first thing what you're supposed to do is we'll add a 1 to the power because we know that we subtracted. And then of course we'd have to divide by the result, 2 plus 1. So if you try to look at that, you're going to have 6x to the power 3 over 3, which will give us what? Which will 3 into 6 is 2, so I have 2x to the power 3. So you've seen that you've reversed, and this is basically what you need to do for basic integration. Not as complicated, right? But again, it becomes a bit tricky because if you try to observe what is happening here is all we're able to get back is 2x to the power 3. We can't get back the 1. And you realize that there are many derivatives of every derivative. By that, what I mean is, if you look at 6x squared, there are likely to be other functions that can also give you that derivative. For example, if you look at y is equal to 3x squared, maybe plus a 1 as well. Okay, you may have another one, maybe 2x to the power 3, but with a different constant. So you notice that they are all actually taking us back to the same thing there. If you differentiate this one, it will give you that. Wait. No, that one won't work. The power is supposed to reduce by, well, let's think of 3x, 2x to the power 3 again, but maybe with a different constant. Yeah, maybe 7. Okay, so the point that I'm trying to make here is basically the constants may vary. So integration itself, reversing that, all we are able to get is only this first part. The constants are not gotten. So that's why when you integrate in such a case, when you integrate 6x squared, what you're going to have is 2x to the power 3. So what you basically need to do is add a constant c. Okay, that's what you do. So that's the basic idea. This is what we call indefinite integrals, because we are not sure what constant was there. Okay, but this is the basic introduction to integration. Let's try to look at different cases or different things that we might expect for different kinds of functions. Okay, so in a case where you have you are told your dy dx, for example, maybe is equal to 2x plus 1, how would you integrate that? So when you integrate 2x plus 1, what you expect is for 2x, increase the power by 1. X is the power 1, so increase it by 1 and then divide by that same 1. And then for the 1, in such a case, when you have a constant, know that x is the power 0, so you add the 1 and then divide by the result as well. So add a constant because we don't know the constant that was there, that was eliminated in the differentiation process. So what we're going to have is 2x the power 2 over 2 plus x the power 1 over 1 plus c, which just gives us x squared plus x plus c. So what we have here is what we call the antiderivative. Okay, now let's look at something different. So we've seen that in a case where you have a constant, in a case where you have dy dx is equal to just, let's say, 2, that's your derivative. If you integrate that, the integral of a constant is just going to be, add the variable, so it's going to be 2x and then plus c. Okay, that's the basic idea. In other terms, again, what we're trying to say is, if you look at the 2 itself, as it's more like it's being multiplied by x, but the power 0, so you need to increase the power of x by 1 and then divide by 1. So you know ones will not make any difference, so it just leaves us with 2x. Okay. Okay, the other thing we can talk about is if your dy dx is just a variable, for example x, you expect, what you expect is the integral of x is going to be what? It's going to be the x that you have is the power 1, so you increase the power by 1 and then divide by the result, which is of course 1 plus 1 is a 2, again plus c, so it gives us x squared over 2 plus c. Then of course things go on and on. Generally we can put it this way: if your dy dx is equal to x to the power n, if that is your derivative, integrating x to the power n is more like you increase the power by 1 and then divide by the result and then add a constant c. That's the basic formula for integration, which is the opposite of what? Differentiation. Now one thing that you need to note is this only works in a case where n is not equal to negative 1. Only when n is not equal to negative 1. Why? Because if n is equal to negative 1, if you've got x is equal to negative 1, and then you get to add a 1 there, and then divide by the result. So this makes it to be undefined. This is undefined. So we are trying to avoid such a case. Notice that I'm not saying that all negative numbers, but I'm only saying negative 1. If you have a negative 2, for example, it's going to work. Okay? But if you have got a negative 1, it won't work. So that's where you say that the integral of x to the power negative 1, which of course is more like the integral of 1 over x, this is now where you get to have a natural log of x. Okay, very important. This applies to all the other cases as well. You may have a case where you have the integral of x plus 1 raised to the power negative 1. Even in such a case, take note, you can't add a 1 and of course divide by result, so it just becomes the natural log of the absolute value of x plus a 1. Okay, now just trying to make things a bit more interesting, the other thing that we know about in terms of differentiation, we've looked at what we used to call, we called it what? We called it the chain rule. So in a case where you have 2x squared plus a 1 raised to the power 4, right? We understand that if you are to differentiate that, the dy dx is going to be the yes, of course, the coefficient you have there multiplied by the 4, you have got get a 4. And then the other thing that we need to do is we need to multiply by the derivative of what is in the brackets. So the derivative of what is in the brackets, in this case, derivative of 2x squared plus 1 gives us what? I believe we have a 4x. So therefore our result becomes 4x, and then you have, oh, 4 times 4x is 4x. I think that is 16x, and then we have 2x squared plus 1. And then of course let's not forget that the power reduces by 1, so it's the power 3, power 3. So basically that's what we have in such a case. So when it comes to the reversing now, assume you are taught to reverse 16x 2x squared plus 1 to the power 3. How would you handle that? How would you basically reverse everything? So in a case where you've got something in the brackets, since one thing that I can think of is we need first of all to add back our power. So if we add back our power, if we add the 1 to the power 3, it becomes the power 4. And then of course we know that initially what happened is we multiplied it with the coefficient, so we would have to divide it. We divide the 4 as usual. Then the other thing that we know is we multiply it by what is inside the bracket, the derivative of what is in the bracket. So here we are going to divide by the derivative of what is in the bracket. So the derivative of what is in the bracket is 4x. Okay, so let's don't forget there's a 16x there. So if we do basically get to divide, on the bottom we're also going to get 16x, so it takes us back to that. So that's how you can reverse some of these certain things. And I think this is where of course you look at more questions like that under your substitution, but that is just like an idea of what you need to know. And then I also introduced you to some of the basic trigonometry differentiation. For example, you've got sine of x, let me put it sine x squared so that you get the basic idea. So we know that if that is your y and then you try to differentiate it, right, your y prime is going to be as follows. So again, take this to be what is in the brackets. So the derivative of x squared is 2x, so you're going to have 2x, and then we'll maintain the entire other part as I believe as it is. So in a case where, but of course this is not correct. So the first thing that you'd want to do is, if you differentiate sine x squared, first of all differentiate sine. The derivative of sine is cosine, so you have cosine x squared, and then multiply by the derivative of what is in the brackets, which is 2x. So the answer becomes 2x cosine x squared. So if you are to reverse it, the reversing of 2x cosine x squared is expected to be as follows. So if you look at the you need to look at this in a certain way. So first of all, of course, there's also going to be a better way of approaching this, but for now we'll try to approach it directly as possible as we can. So if you look at it in this way, you know that the integral of cosine is what? The integral of cosine is sine. So we have sine x squared. Now the other thing that you know is when you are basically differentiating, you basically multiply it. So here we'll divide by the derivative of what is there. So the derivative of that is what? It's 2x. So that will go. Now of course we'd have to add a constant c, because we do not basically know if there was a constant initially there, even if we in this case we're clearly able to see what was there. So in other terms, the general way of looking at this is, if you have sine mx, the integral of that is expected to be, what you need to do is we are going to But of course, in this case, where we've got sine, the integral of sine, we understand that the derivative of sine is cosine, right? So the integral of cosine is sine. Now we know that the derivative of cosine is negative sine. So if we are to integrate a positive sign, it's like we're reversing. We expect that it's going to be a negative cosine, right? So we're going to have a negative cosine. Mx is going to be maintained. And then we are going to divide by what? We're going to divide by the derivative of what is in brackets. So it's more like 1 over the derivative of what is in brackets, which is just like m in this case if you've got mx there. If you've got mx squared, it will be 2m, and then of course plus a c, which is clearly what we also had in that case. So one thing that you're noticing, one thing that you're seeing is, for the sake where you've got the trigonometric functions, it's like what we have is the u substitution as well, or what we have is the chain rule. So we'll reverse it the same way. Now going back to these guys, which are very interesting, the exponentials and whatnot, one thing that you are able to remember is when we were dealing with the integral of let me say the derivative of exponentials, if you've got e to the power 2x, one thing that you know is when you look at that, you expect that the derivative, or short, sorry, yes, the derivative is going to be, you need to maintain it, and then of course what you do is you multiply by the derivative of the power. So the derivative of the power is 2, and then of course natural log of e as well, which is the base in this case. Of course in this case it will be eliminated, so you're going to have 2e to the power 2x. Now if you are to reverse this, the opposite is true. So what we basically get to do to reverse is the integral of an exponential function is as simple as dividing by the derivative of the power. So we're going to have 2e to the power 2x, and then we'll divide by the derivative of the power, which is of course a 2, which will give us back our e to the power 2x. But of course we need to add a constant because we are not sure if there was a constant available or not. Okay, so basically this is our introduction to integration. We'll proceed and just look at the way we can look at integration as a summation and indefinite integrals. Okay, so before we get to look at definite integrals and areas under the curve, let's look at indefinite integrals. So what are these? So we've already established to say when you look at a derivative of any given function to be, for example, 2x, and then they ask you to integrate. So the integral of 2x is of course going to be 2x, and then add the power by 1, so it will be to the power 2 divided by 2. So realize that your answer will become x squared. Now one thing that you're not sure of is you don't basically know the original function where this came from. The chances are it had a constant. Okay, now we don't know the exact constant that was there. Okay, I'm giving you some of the possible options. Okay, so what you basically do is you need to just add a constant c. So this is now what we call indefinite integrals because of that constant c, which is called the constant of integration. And I believe there's nothing more that you need to know about indefinite integrals, just the idea of you adding a c if you differentiate or if you integrate something. So let's look at some few examples. Determine the indefinite integral of 12x squared minus 14x plus 12. So how do you go about that? So the integral is going to be, of course I've said, increase the power by 1. So for the first one it becomes 3, divide by that. And then for the second one as well, increase the power by 1, it becomes 2, divide by that. Again for the other one where there is such a constant, just add the variable. Since it's like you have to the power 0, so if you add the 1 you just become the power 1, and then if you divide by 1, no change is expected. So of course 12x to the power 3. Why did I forget that? So 3 into 12 is 4, so we have 4x to the power 3 minus 7x squared plus 12x. Now we don't know if it was a constant, so we'll put plus c. These are what we're calling indefinite integrals. So you may have different examples. You may have other examples that you've looked at, other different types of integrals that you have. So for example, integral of what? So we've said the integral of exponentials, what you basically get to do is divide by the derivative of a power. So e to the power 2x will divide by 2, and then of course natural log of a base, which in this case is e. Now natural log of base e is just the 1, so you're going to have e to the power 2x over 2. Okay, now do we just end there? So we'd have to put plus c, because we don't know if the original one had a constant. So this is what we are calling now indefinite integrals. So you may have others as well. You may have the trigonometric functions. They can also give you these other functions, x to the power 1 over 2 as well. Of course, all these are, we're differentiating them in respect to x. So in such a case, we know that the integral of sine is, because we know of course one thing that I like, the derivative of sine is cosine. The derivative of cosine is negative sine. So in this case, we are reversing, so it's like we're starting from this side. So if you have negative sine, it gives you positive cosine. So if you have positive sine, it's supposed to give you negative cosine. So you're going to have negative cosine of 3x, and then we're supposed to divide by the derivative of what is there. So 1 over 3 plus c. So basically what comes out there is negative 1 over 3 cosine of 3x plus a constant c. Okay, then looking at the last example there, feel free to pause the video and just try it out. So this is a case now where you have a power of half. So if you add the 1, of course you expect you're going to get 3 over 2, right? 3 over 2. Okay, so you understand dividing by 3 over 2 is as good as multiplying by 2 over 3. Okay, so you're going to have 2 over 3 x to the power 3 over 2, and then plus a constant c. So these are examples of indefinite integrals. Let's proceed and look at definite integrals. But of course, maybe before I go, I need to mention that you are also capable of finding the value of x. Okay, you are capable of finding the value of x. To make it, let's consider a case where they've asked us to integrate x squared. So if you're asked to integrate x squared, let's assume the original function here was 4, right? It was a 4, and then so expect that if your y is that, and then if your value of x is a 1, if your value of x is a 1, or maybe let's take it if the value of your x is a 2, if your value of x is equal to 2, expect that y is going to be what? 2 squared, so y will be equal to 8. So if they've given you a coordinate 2, 8, and then they ask you to integrate x squared, given that the original function cuts through or passes through that line, so you're able to find c. Let's try to see how. So if you try to integrate x squared, you're going to have 2 plus 1, which is of course a 3, and then divide by that 3, so it will be plus c. So this becomes your y. Y is equal to that. And of course I'm wrong, yeah? I'm wrong. Why am I wrong? Because I was taking x squared to be the original function. So yes, I'm wrong. So let's take it this way. Let's instead have x. So if you have x, the integral of x is going to be x to the power 2 over 2. Wait. No, how is it the power 2? Yes, 2 to the power 2. So obviously I'm still wrong anyway. Let's go back to this form. Okay, so let's assume the constant itself was x to the power 3 over 3, and then plus, let's say, a certain constant 2. Let's say this is the original function. So in such a case, if we had to have a value of the value of x to be 3, yes, the value of x to be 3. If it is 3, we expect to have 3 to the power 3 over 3 plus 2, and then of course 3 to the power 3, that is going to give us like what, 20. Okay, let's just assume we have 3 times 3 times 3. So that will go. You remain with 9. 9 plus 2. 9 plus 2 is what? 11. Okay, so in such a case, the coordinate will be 3 over 3, 11. So if you are told you don't know what the constant was a 2, you can find the value c there. How do you go about that? So what you just basically do is plug in 11 is equal to plug in 3 over 3 plus a c. So you have 11, and then you have minus 9, and then equal to c. So c is equal to 2. So in such a case, you're able to find the actual value of c if they give you a certain coordinate. And look out for such questions. They are free marks questions. I didn't edit. I won't edit because I want you to see that I can also make mistakes. Okay, so there we are. Okay, let's talk about definite integrals. We've already looked at indefinite integrals where we don't have limits. So in a case where you have limits, those are called definite integrals. So for example, if you've got a b and an a down there of a certain function in respect to x, this is called a definite integral. So b is called the upper limit, a is called the lower limit. So you understand basically this will simplify to something where the integral is inside the brackets and then the upper limit becomes b and then a. So what will happen is taking the integral of f of x to be, let's say, capital F of x, that would mean that at every point where you've got x after the integrating, you're going to have f of b, which is the upper limit, minus f of a, where the function capital F represents the integral. So let's just go into it. Consider a case where they want us to look at a case where we have 4 and 1 as the limits, and then x squared. So the first thing that you'd want to do is first of all to determine the, of course this is in respect to x, the first thing that you want to do is basically get to determine the integral. So the integral is going to be, so increase the power by 1, so it will be the power 3 divided by that, and then of course we will just add a constant c. Okay, so don't forget the limits. The limits, we have got a 4 and a 1. So now what happens for you to evaluate that is at every point where you have x, substitute the limits. So we start with the upper limit. So if you substitute a 4 there, you're going to have 4 to the power 3 over 3 plus c in brackets minus the lower limit where we have 1. So put the 1 where there's x over 3 plus c. So you will notice that of course c is common and to subtract. So 4 to the power 3, that is 4 times 4, 16 times 4, 64. So I have 64 over 3. The c's will subtract, and then 1 to the power 3 is just a 1 over 3, which of course will reduce to 63. Am I right? 63 and then over 3. So 3 into 6 is 2 and then 1, so 21. So this applies, the limits may be negatives, they may be positives, all the same. So for on practice, try out this one, pause the video and just try it out. So obviously, you know, the integral is going to be what? If you integrate x to the power 3, you're going to have x to the power 4 divided by 4. Now at this point, you know that it's not necessary for us to add the c, but because it will always be subtracting, so we have 3 and then negative 2 as our limits. So for the first part, use the upper limit, which is 3. Now raise the power 4 over 4, and then minus. Now we'll put the lower limit, which is now negative 2, the power 4 over 4. Okay, as simple as that is. So if you try to simplify that, what you get is the answer. So limits may also apply to, we looked at trigonometry functions, right? So you may have it in terms of angles, like that, where you have got cosine of x dx. How do you approach such one? So in such a case, of course, we'll still do the same. Just perform the normal way. What's the integral of cosine? So the integral of cosine is reversing what was differentiated. So we know that the derivative of sine is cosine. So obviously, in this case, the answer is sine. So you're going to have sine of x. Of course, we know you divide by the derivative of what is in the brackets. The derivative of x is just the 1. So in this case, nothing changes. And then we have upper limit to be pi over 2 and then 0. So you're going to have the first upper limit, which is sine pi over 2, and then minus sine of the lower limit. Now sine pi over 2 is the same as sine 90, which is the 1. Sine 0 is 0 because the graph starts, I believe you are conversant with trigonometry, so at 0 there, and then this is pi over 2, and that's the 1, negative 1. So the answer is just the 1. So for your own practice, try to attempt to look at these few questions. Try to determine the definite integral when you have 1 and 0 for e to the power 2x, and then you can also attempt to try out the definite integral when you have 1, negative 1, and then 5x to the power 3 dx. All these are in respect to x. So feel free to pause the video before you basically get to see the results or the solutions. Okay, so you can also attempt to try out where you have pi over 2 and then a 0 now in terms of sine. Okay, so the results that you need to expect after you've done all your calculations are as follows. So you need to have a 1 there. Then for the other one, 5x to the power 3, you need to have a 0. And then the other one, e to the power 2x, you need to have e to the power 2 over 2 minus half. Okay, so hopefully you're able to determine that. So now let's proceed and look at the application of definite integrals. So in terms of where you've got a graph, how do you find the area and the curve, and then look at the volume as well. Well, let's proceed and just look at the integrals of logarithms and exponentials. Just within 5 minutes, we'll look at 1 or 2. So we've already established to say integration is like the reverse or anti-differentiation, or the opposite of differentiation. So we'll approach this in such a way. So I've already told you to say, when you look at y is equal to e to the power 2x, so one thing that we were doing to differentiate that, we are basically saying our derivative is going to be whatever you have, get to divide by what? Get to multiply by the derivative of a power. So the derivative of a power, so first of all maintain what we have, and then multiply by the derivative of a power, which is a 2, and then natural log of a base. So now, of course, in a case where we've got an exponential, that is not necessary because it becomes what? 2e to the power 2x. Okay. So the opposite of that is you understand that, okay, well, if that is the case, if integration is the opposite of differentiation, if I've been given the integral of 2e to the power 2x, one thing that you'd have to look at is, okay, well, since I've got an exponential function and since integration is the opposite of differentiation, since for differentiation I multiply by the derivative of the power and then natural log of the base, what is going to happen is this time around I'll divide. So if you have 2e to the power 2x, you are going to divide by the derivative of the power, which is a 2, and then of course natural log of a base plus a constant c. So here what you can see is 2 and 2 will divide, and you know that the natural log of e is a 1, so what remains is e to the power 2x plus what? Plus c. I think this is proof enough to say integration is actually the opposite of differentiation. So, well, if that is the case, how about in a case where we can have a look at y being equal to 2 to the power 2x, for example? In such a case, what might you expect there, or what should you expect? So in this case, you know that if you are to look at your y prime, you expect that the derivative in this case is going to be, again, we'll multiply. First of all, maintain what we have, 2 to the power 2x, and then we're going to multiply by what? The derivative of the power, which is a 2, and then of course natural log of the base, which is just that. Okay, so if we are to reverse that, what do we expect? So the reverse of that, which is like expected with the integration, of course what we have there is we have 2 to the power 2x multiplied by a 2 multiplied by natural log of 2 as our derivative. So for integration, we're going to basically do the opposite. That is, we'll divide the entire thing by what? By the derivative of the power, and then divide by the natural log of the base as well. So that goes away, that goes away, this goes, that goes. So it takes you back to that, plus c. Okay, so at least we are now getting the idea there. So integration is the opposite of what? Integration is the opposite of differentiation. Now, so we've looked at a few examples under exponentials. Let's try to look at logarithms with what's going to happen. So if you have got y is equal to natural log of, let's say, 2x, right? Yes, let me start with x squared. Let's say x squared. Okay, let me use x first of all. There's a reason why I'm trying to use x. So if I use natural log of x, one thing that we know that the derivative of that is going to be the derivative of natural logs or logs is, first of all, the derivative of what is in the brackets, which in this case is equal to a 1 divided by the actual, which is just x. Of course, we understand that we're also supposed to put the natural log of the base e. But in this case, what you can see is what? Natural log of e is just equal to a 1, right? Okay, so it's not necessary for us to show that. So we have 1 over x. So this is a case now where I was saying that if you have a case where you have 1 over x, the opposite is just natural log of x. This is what I was trying to say. So this is where it comes from. We know that from the derivative, it is going to be like that. And I think this can be backed up by another example. If you have y is equal to natural log of x squared, your y prime is going to be, the derivative of what is in the brackets there is 2x, and then divided by x squared itself. Okay, so there, what do we expect in this case? In this case, what we are going to have is our y prime will reduce to the x is common, so I have a 2 and then over x. So the opposite there is the derivative of 2 over x. We can pull out the constant so that we have 2 and then the integral of 1 over x. Now the integral of 1 over x is what? Is just natural log. So we have natural log of x. Now you know that according to the rules and algorithms, this can go back as a power there. So you have got natural log of x to the power what? X to the power 2. So you can clearly see to say when you have 1 over a variable raised to the power 1, or in other terms the variable raised to the power negative 1, the opposite is the natural log. Okay. Now just one more example that we'd have to look at, that is under logarithms. Now what about a case where you have these bases, let's say x squared? In such a case, we know that our y prime in such a case, again the derivative of what is in the brackets or what is attached to the log is going to be 2x divided by, what are we going to divide by? The actual function itself multiplied by the natural log of the base. In this case the base is what? Is 2. Of course for the natural log we know the base is e. That's why even if you say natural log of e, it will disappear for the other ones from looking at. So of course in this case this will reduce to 2 over x natural log of 2. So the question you might be asking yourself is, what happens if I want to reverse that? Or if I've been given 2 and then x natural log of 2, how do I basically get to integrate that? So we are saying the opposite. We basically get to do the opposite, right? Okay. So what you want to do is, since you know that for differentiation what was happening is you were basically looking at, if you look at the numerator there, it is as a result of the derivative, right? So the derivative there. So how do we get to move from this part and then go back to that part? So you can pull out the constant, which is a 2, and then we have 1 over x, and then we can split as well. We have what? 1 over natural log of 2. 1 over natural log of 2 I believe is a constant, so we can actually pull it out as well. So let's pull it out so that it can be outside. So 2 over natural log of 2 as a constant, and then we understand that 1 over x, if you basically get to integrate that, you're going to get the natural log of x. So reduce to 2 natural log of x over natural log of 2. Now of course we understand that the rules of logarithms tell us that this can be expressed as natural log of x to the power 2 over natural log of 2. So of course this is equal to that. Okay, so you may not understand right now, but if you've done the conversions of bases, okay, let's try to do it for the sake of having fun here. We can still convert the natural log back to base 2. So what you need to do is, if you're converting, so if you convert the top part there to base 2, you would have to say log 2 in base 2. So you get first of all the top part, and then you again the same base, log 2, now with the base of natural log is e. So we are going to divide. So divide, what are we dividing with? The converting natural log of 2 to base 2. So the base is e. So again we're going to have log 2 of 2 and then log 2 base e. Now dividing is as good as multiplying by the reciprocal. So if we do multiply, there will be an exchange. The e part goes on top and then the 2 goes down. Of course that is equal to a 1. This and this will divide. So we are going to have only log 2 of x squared remaining. So you can see clearly to say indeed integration is the opposite of differentiation. So this tutorial we're just going to go over integration by substitution. So I've got up to 14 questions that we're going to answer, beginning with this question, ending up to that question. Okay, so there are a lot of questions in between to do with trig and other things that will require us to deal with integration by substitution. Okay, so integration by substitution, we usually use the letter u to perform substitution. So this applies to functions we can't basically deal with as we do with simple functions as 6x. For example, if I ask you to integrate, it's going to be something direct. Just add a 1 to the power and then of course divide by the result, right? It ends there. Now for a complex function as this one, in other terms, I usually like thinking of it as integration by substitution applies to anything that you differentiate by the chain rule, right? Okay, so I'm sure you know what the chain rule is. So let's just get into it. So what basically happens is we substitute by u as our preferred letter. Okay, so in this case what we're going to do is we'll look at what's in the brackets and when we equate it to u. So let u be equivalent to x plus 5. And then on our next step, the integral of what is in the brackets, we're going to put a u and then the power 6, right? And then we have dx there. And then at that point, what do we expect to have? So let's try to integrate this. Du dx is going to be, what that means is we're differentiating the equation in respect to x, du dx, right? So in other terms, du is going to be, what's the derivative of x? Derivative of x is 1, right? Derivative of a constant is 0. So of course du dx, right? So this is what we have. And then we need to substitute dx there, right? So we have to make dx a subject. So let's cross on multiply. We're going to have du is equal to 1 multiplied by dx. And then of course 1 can be divided the other side. I'm just trying to show you that, but there's no difference. Okay, so where there's dx now we can substitute. So we have u to the power 6, and then where we have dx we're going to put du, right? So this will now allow us to simplify this. So this is something easy to integrate, right? We're able to integrate u to the power 6. How do you go about it? So what's going to happen is you will add the 1 to the power just as we did. So 6 plus 1 is 7, so we divide by the same result. Okay, and then of course add the constant c. Anything else? So we can take back our u. Our u was x plus 5 from the start. It will now be the power 7 divided by 7 plus c. So that is our result after integration. I think one thing that you've seen here is what we're basically dealing with is we're just putting a u where what we have in the brackets, and then thereafter we need to substitute this with du, and then we're good to go. Let's try to see what we're going to have for the next question. Now let's assume we have the integral of 9 plus x to the power 2. So feel free to pause the video and try this one out. So all the same, we'll let our u be equal to what is in the brackets, 9 plus x. So our integral, what is in the brackets, we'll put a u and then the power 2 and then dx. So we said substitute the dx by du. So the only way we can do that is by differentiating the other equation we have. So du is going to be, derivative of a constant is 0, derivative of x is 1, dx, right? So make dx a subject, so dx of course will still be equal to du over 1 if you over 1 it's just like nothing. So we have integral of u squared, and then for our dx we now have just du. So we can differentiate that now. We can actually integrate. So u squared, we'll add the power 1 divided by the same result, 2 plus 1, and then plus c, which of course our u, we know it was 9 plus x from the start. Yeah, the power 3 divided by 3 plus c. That's our result. And let's look at a different kind of a question where we're dealing with trigonometry. The integral of cosine and then 3x plus 4 dx. How do you integrate this? So I want you to pay attention to a few things. One thing that you need to know is the derivative of sine x is cosine of x. The derivative of cosine of x is negative sine of x. So integration is the opposite. It's the opposite. It's the opposite. If you get that, you're good to go. So all the same here, we'll let our u be equivalent to whatever is in the brackets, right? So let our u be equal to 3x plus 4. So I have our integral of cosine of u and then the x. So let's go ahead and differentiate whatever we have. So our du, our du is going to be equal to derivative of 3x is 3, derivative of a 4 is this is 0. So of course dx. Let's make dx a subject. So divide both sides by 3. So du over 3 is equal to dx. We can go back to our equation. Where is dx, we'll put what we found there. So cosine of u and then du over 3. So whenever we're integrating, we're allowed to pull out the fraction. So the fraction we have in this case is 1 over 3. So we'll pull it outside the integral. And then for the integral, we're going to remain with cosine u du, right? So at this point, we're at liberty of now integrating. So we have 1 over 3. What's the integral of cosine of u? So this is what I was trying to tell you. I said the derivative of sine is cosine. So when I ask for the integral of cosine, you are reversing. So the integral of cosine is sine. Okay? So we have sine u, right? And then plus what? Plus the constant c there. So write the final answer on top. So it's going to be 1/3. Now sine what? Our u we put back, our u we equated it to be 3x plus 4. And then of course plus sc. So that's our integral. Let's look at another trigonometric function. So you're at liberty of pausing this one and trying it out. Okay, so pause the video and try this one out. Okay, so all the same, we'll let our u be equal to what is in the bracket, 7x minus 3. We'll differentiate it right away. Du is going to be 7 after differentiating 7x minus 3. Of course, dx. We can make dx a subject right away. Okay, and then here we can now use substitution. Whatever is in the brackets, we equated it to be equal to u, so let it be equal to u, and then dot dx. So now where is dx, we can put that du over 7. We can pull out our 7. Since it's a fraction, it's 1 over 7. So we have 1 over 7, the integral of sine u du. Okay. What's the answer there? What's the integral of sine of u? So I told you to say the integral or the derivative of sine is cosine. I also said derivative of cosine is negative sine. So therefore, if we are talking about the integral of sine, it's like we are saying we have got positive sine, right, as the derivative of something. So it's obviously going to be the opposite of this. So it's a negative cosine of x. So the integral of sine is negative cosine. So we have 1 over 7 and then negative cosine of u plus c. Okay, so our final answer therefore is going to be negative 1 over 7 cosine. Our u is 7x minus 3 plus our c. That's our answer. Okay, so we've moved away from the trig examples. Let's look at now these are the interesting questions. Let's say we have the integral of 1 over 1 minus 2x dx. So we'll let our u be equal to the denominator. So our u is equal to 1 minus 2x. So our du is going to be negative 2 dx. Okay, so the dx of course just shows us that we've differentiated in respect to x. So let's make the same dx a subject. So du over negative 2 is equal to dx, right? So here we're going to have the integral of 1 over our u, since our 1 minus 2x is equated to u, right? And then for our dx, we're going to put du over negative 2. So straight away pull out the negative 1 over 2. So it's negative 1 over 2. Since our negative 2 is on the bottom, so it's negative 1 over 2. And then we have 1 over u multiplied by du. So what's the derivative of 1 over u? This is something that is very important. So if you look at u, when you look at 1 over u, this is the same as u to the power negative 1. You take it to the numerator, right? Now if you do that and then add the 1, it's going to give you a 0, which you can divide with. So mathematically, the integral of any letter raised as a denominator raised to the power 1, this is equal to the natural log over the same denominator. So the integral of 1 over u is basically natural log of u. Even x, natural log of, the derivative of 1 over x, or the integral of 1 over x is natural log of x. Very important. Okay, so plus c. Now this can reduce to negative half natural log. Now for our u is basically equivalent to 1 minus 2x plus c. That's our answer. So pause the video and try this one out. We have 1 over 7x plus 5. What do you expect to be there? The integral there. So straight away, let our u be equal to the denominator, 7x plus 5. Our du is going to be 7 dx. That's our derivative. Let's make our dx a subject. So our dx is equal to that. Let's proceed. The integral of 1 over our u, okay, since our u is equal to that, and then for our dx, it's equal to this du over 7. So pull out the 7 which of course we know is 1 over 7. And then we have the integral of 1 over u again, and then du. So this is going to be straightforward. So 1 over 7 natural log of u plus c, which is of course 1 over 7 natural log, our u in this case is 7x plus 5, then plus c. Alright, good. So let's look at an exponential kind of a question. The integral of e to the power 3x minus 2 dx. Okay, so as you might guess, u is going to be equal to that. So our u is equal to 3x minus 2, right? And then our du is going to be 3 dx. So our dx is going to be equal to this after dividing by 3. So if we move there, if we proceed, we have an integral of e to the power u, and then for our dx we have du, right, over 3. We can pour out our 3 which is on the bottom, so 1 over 3, and then we have got e to the power u du. So here what we're doing is we're integrating our exponential. So one thing that you need to know is, if you're integrating e to the power x in respect to x, the answer is always going to be e to the power. It's always going to be e to the power x. Okay. So integration, differentiation, it will still be the same. Okay. So the basic idea that you should know is, if you have e to the power u and then you're integrating, it will still be e to the power u. Just know that. Differentiation as well, it's still the same. Still the same. So therefore, we have 1/3. So we've integrated this. If we integrate, it will still be the same. So it will still be e to the power u plus c, right? So this can actually be expanded as 1 over 3 with our e raised to the power 3x minus 2, and then plus a constant c. So that's our answer there. Okay, let's move. Let's look at the other kinds of questions which are interesting. Let's say we have integral of 2x multiplied by 1 plus x squared. This is a very nice question, right? How do we approach this one? How do we approach it? So here we'll let our u be equal to what's in the brackets, right? Under the square root, sorry. So let our u be equal to 1 plus x squared. Hopefully it gives us something unique. So our du is going to be 2x dx. Let's make dx a subject, so it will be equal to du over 2x. Can proceed here. The integral of 2x, and then under the square root we have a u, and then multiply for our dx. Our dx is equal to this part. So our dx is equal to du over 2x. So you can see that the 2x can actually divide, right? So the integral of root of u and then du. What's next? So at this point we're integrating the root of u. So the root is the same as the power half. So add a 1 to that. So we're going to have u the power half plus 1 divided by the result. Of course that's going to be 3 over 2. And then plus constant c. So now some of you already know that simplifies too. So dividing by 3 over 2 is the same as multiplying by 2 over 3. So it just be 2 over 3. And then for the top it will be u to the power 3 over 2. And then plus a constant c. Now this is just the same as 2 over 3. U is what now? So our u is 1 plus x squared. Alright. The power 3 over 2 plus c. You can even draw a line here so that it makes more sense that way. So that is basically the integral of the question we had. Okay, so with that in mind, feel free to pause the video and try this one out. Integral of x squared and then this root of 2x to the power 3 plus 4 dx. Try this one out. So you will let our u be equal to 2x to the power 3 plus 4, and then our du is going to be 3 times 2 is 6, so I have 6x squared dx. Alright. And then so if we make dx a subject, it's going to be equal to du over 6x squared. Okay, so on the next step now, so our integral of x squared, where is the root, we are putting a u under because we've said let our u be equal to that. And then for our dx is equal to du over 6x squared. So at this point the x squared can actually divide, and then we can pour out the 6, so 1 over 6. Alright, because it's on the bottom, it's a denominator, so 1 over 6, and then we have root of u and then du. At this point you're able to simplify this, right? So you already know 1 over 6, and then the root of u is the same as u to the power 1 over 2. So add the 1 and then divide by the result, which is 3 over 2, okay, plus c, right? So that is simple there. So what do we have? So obviously dividing by 3 over 2 is the same as multiplying by 2 over 3. So we have 1 over 6, and then we have 2 over 3, and then we have u to the power 3 over 2, right, plus c. 2 there is 1, 2 there is 3. So we have 1 over 9. Yeah, 1 over 9. And then for our u, it is equal to 2x to the power 3 plus 4. Now raise to the power 3 over 2 plus c. That's the result there. Okay. I have now a very interesting question. The root of 4x over the denominator, the root of 2x squared plus 1. So just to test your understanding of what we've looked at so far, we've looked at a lot of questions, over 10 questions. So be at liberty of pausing the video and just trying this one out to see what if you're able to answer it. Okay, so if you're tired, feel free to take a break and come and continue watching the video. I'm actually taking a cup of water right now. Alright. So if we've answered it, we can now solve it. So how do you answer this one? So obviously the same way, let our u be equal to the denominator under the square root. So we have 2x squared plus 1. If we differentiate that, we're going to have 4x, right, dx. If we make dx a subject, it's going to be equal to du over 4x equal to dx, right? If we proceed on the left, 4x is our numerator, our denominator will now have root of u, since we've said let our u be equal to 2x squared plus 1. and then for our dx, it's equal to this part, so du over 4x, right? So the 4x will go. We have the integral of 1 over root of u and then du. Okay, so at this point we can take our u on top, so that it will be 1 over root of u is the same as 1 over u to the power half. Okay, du. Let me take you back to the top. So this part, we can take the u on top so that it becomes the power negative half. Okay, and then du. So to integrate that, u is going to be, we're going to add the 1, so plus 1, and then of course the same. Now negative half plus 1 is the same as 1 minus half, which is just like dividing by half, and then we have got plus c. What becomes our answer there? So on top we're going to have u to the power half. Negative is also going to be the power half. So u to the power half is the same as the square root. So whatever I'm doing there on your paper, I would expect you to have written different steps. Okay. So the root of u is going to be the square root of 2x squared plus 1, because that's what our u is, and then over half. Now dividing by half is the same as multiplying by 2 over 1. Okay, so I'm multiplying by 2 over 1, so just multiplying by 2 in other terms, and then plus a constant c. So that's our answer. That's the answer we expect after integrating the question that we had. Let's look at another kind of a question. The integral of x over the root of x squared minus 9. Alright, so feel free to pause the video and try this one out. So let our u be equal to this, whatever is in the denominator, square root, so we have x squared minus 9. If we differentiate that, du is going to be 2x, right? If we make dx a subject, we have du over 2x is equal to dx, right? So then we have the integral of x over, so for our denominator we've said our u is equal to that, so we have root of u, and then for our dx is equal to the first part, so we have du over 2x. So our x can actually go, and then you can pull out the 2 which is on the denominator, so we pull out a half root of, so remaining with the root of 1 over root of u and then du, which of course is the same as 1 over 2. If it goes on top, it will be u to the power half, negative half actually, negative half. What else? Du. So we know what we expect as a result there. So we have half. So for the integral there, the u is going to be now negative half plus a 1, and then we'll divide by the same result, which is of course again a half, right, plus c. So we have half. So in the brackets we now have, for the top part, negative half plus 1 is half. That's the same result I'm dividing with. So the half is the same as the square root, so we have the square root of our u plus c. Now don't forget that we're dividing by half again. So dividing by half, I said it's the same as multiplying by the reciprocal, which is like 2 times 1, or 2 over 1, sorry, multiplying with the 2 over 1. So at that point a 2 and the 2 divide, then we have root of u. So our u is x squared minus 9 plus c. So this is our integral for that question. Okay, so we're advancing. Let's look at question 12. This should be question 12. So integral of x over root of 4 minus x squared. How do you answer this one? How do you answer it? Okay, so we'll go over several practice questions under integration by parts. So the formula we're going to be using is u dv equal to uv minus the integral of v du. Okay, so we'll look at questions where you can't use substitution. Questions like x squared, natural log of x. How do you integrate such questions? We'll look at integration of trigonometric functions like sine inverse of x. How do you determine the integral? How do you determine the integral of x squared? Cosine of 4x. How do you integrate x squared e to the power 3x? So these are just samples of several questions we're going to go over. Okay, so one thing that you need to understand is each time you're dealing with integration by parts, we basically decide u most as the first one. We prioritize it. So we use letters L, I, A, T, E to help us pick the one that's going to be easier. Okay, so what you basically get to do is in each question you're given, first of all identify your u by using these letters. Okay, after you identify your u, so let's use an example to explain whatever I'm saying. So for the first question, we have the integral of x e to the power 2x. Okay, so using our letters L, I, A, T, E, I can pronounce that as liate. So if you have that, and then you know this stands for logarithms, that stands for inverses, A stands for algebraic functions, T stands for trigonometric functions, and then E stands for exponentials. So in this case, x is algebra and then E is an exponential. So exponential is the last one. So the first one, the one that's coming earlier, is A, which is algebra. So we'll let our u, therefore our u is going to be equal to x, and then obviously if you pick your u, the remaining part automatically becomes dv. In this case it's e to the power 2x. So we have to determine the other remaining parts. So if we have our u, we need to determine our dv, and then if we have our dv, we have to determine our if we have our u, we have to determine our du, and then for our dv we need to determine our v. Okay, so whenever you have a d in front of something, just know that that's already differentiated. Okay, so in this case where we have du, we have to differentiate x. So a derivative of x is what? Derivative of x is 1. On this other part we have e to the power 2x, so this is already differentiated because having a d, so we now have to integrate it. So integration of exponential functions require you to divide by the derivative of a power. So e to the power 2x, what's the derivative of 2x, which is the power of our exponential function? So the derivative of 2x is just a 2. So I have to divide by a 2. That's for integration. For differentiation of an exponential function, you multiply by the derivative of a power. Okay, so at this stage now we are ready to substitute into the equation. Okay, we can now substitute. So therefore our integral is going to be, so our u is x, our v is e to the power 2x over 2 minus the integral of v. So our v is what? Again exponential, 2x over 2, and then our du is just the 1. Okay, so we can finish it up. So our answer becomes x e 2x over 2. Now the integral of an exponential function, I already said you divide by the derivative of a power. So the derivative of 2x is still a 2. So it's going to be minus e to the power 2x. Now we're dividing by another 2. So 2 times 2, okay, which will give us a 4. But I won't multiply because I would love to factorize. So if you want, you can just put a 4 there and that's your answer. But I want to make it look more simplified. So my answer can be, so e to the power 2x over 2 is common. So for the first part, x will remain, and then for the other part, to be 1 over 2 remaining. Okay, so that's our derivative. Simple, right? Okay, let's look at some more. Let's say we have the integral of x e to the power negative x. So I've already highlighted to say the first thing is your formula is the integral of u dv is equal to uv minus. Now you notice that what comes here is the opposite of what you started with, so it will now be v du, right? So obviously this is going to be the same. We use LIATE to help us identify u. So in this case, it's still algebra and exponential, so a, therefore our x is u because it's an algebraic function, right? So therefore our u is x. So if our u is x, our du is automatically 1. So if our u is x, it means our dv is the remaining part. So therefore our dv is the exponential e to the power negative x. So our v, which is the integration of that, is going to be e to the power negative x. We have to divide by the derivative of the power. The derivative of negative x is automatically negative 1, which reduces to just negative e to the power negative x. So we have this equal to uv. So our u is x, our v is that, which is just negative. So negative e to the power negative x, and then minus the integral of v. Our v is still that, negative e to the power negative x multiplied by our du, which is just the 1. Simple, right? So what do we have? So we have negative x e to the power negative x minus, so the integral of that again, you're just going to divide by the derivative of a power. So the derivative of a power is negative 1, so it's going to be negative e to the power negative x divided by negative 1. Okay, so you end up with a positive. So negative x e to the power negative x minus e to the power negative x, because inside there we already have a positive, so positive by the negative will now will remain a negative. So if you want, you can still factorize e to the power negative x is common, and then you remain with, you can pull out a negative 1 actually, a negative, so to remain with a positive x and then plus a 1. And let's say we have the integral of x sine of x. Okay, so at this point we do know our formula. It's u dv being equal to uv minus the integral of v du. Okay, so let's have it there. So what do we expect there? So let's not forget our priority for u. Okay, so logarithms, inverses, algebra, trig, exponential. So in this case we have trig and algebraic function. So the algebraic function still comes first. So therefore our u still stands to be x, and then so the remaining part is going to be dv. So our dv now is going to be sin x. Okay, so we can determine now our du. So our du is the derivative of x, which is 1, and then our v, which is the integral of dv. So what's the integral of sin x? So it's negative cosine of x. So I usually remember this because I know that the derivative of sine is cosine of x. Derivative of cosine of x is negative sine of x. So the only way we can have a derivative being sine of x is when you have derivative of negative cosine of x, because it's positive gives us a negative. Okay, so here we are. We can now substitute. So our u is x, our v is negative cosine of x, and then minus our v is negative cosine of x, and then multiply by du, which is just like a 1. So this becomes equal to negative x cosine of x, and then minus negative cosine of x. So what is the integral of negative cosine of x? So the integral of negative cosine of x, or the integral, think of it as the integral of cosine of x is sine of x, because the derivative of sine of x gives us cosine of x. So the negative will also give us what? Negative sine of x. Okay, so that gives us negative x cosine of x plus sine of x. Okay, of course don't forget plus c. In the past 2 questions we've forgotten to add plus c, so after integration we always add a constant c. Okay, let's move. Let's say we have the integral of x squared natural log of x. Okay, so in this case we have natural log, which is log, so it's going to be our u. So our u is natural log of x. So we can determine, so the remaining part of course is dv. So our dv is x squared, right? So of course we can start by determining the du, which is going to be the derivative of natural log of x. So how do you differentiate the natural log of x? So you differentiate natural log of x by u prime over u, as simple as that is. So our u prime in this case is just derivative of x is 1 divided by x itself, so 1 over x. If we had x squared, it is going to be x on top divided by 2x, which reduces to reduce to what? Sorry. So we'd have the derivative on top. If we had x squared, it's going to be 2x, that's the derivative, divided by x squared, which will now reduce to 2 over x. Okay. And then what's the integral of x squared? So add the 1 to divide by that. So our v becomes x to the power 3 over 3. Okay. We can now substitute. So we have uv. So for our u we have natural log of x. Our v we have x to the power 3 divided by 3, and then minus the integral of our v, which is x to the power 3 over 3, and then our du is just 1 over x. So this will reduce to natural log of x. So we can start with the algebraic function preferably. So we have x to the power 3 over 3, and then natural log of x minus. So the integral of the x can divide with an x there, can remain with x squared over 3. So just one more step, we can just integrate this part. So we integrate by adding a 1 to the power and then dividing by the result. So if we add a 1, it's obviously going to give us a 3, and then we'll divide again by the 3, which will now give us a 9. So we have x to the power 3 over 3, natural log of x, and then minus, the power will become 3, and then we'll divide by an extra 3 now. So I've left it in that form to just show you that we can still factorize if we want to, right? So what's common? X to the power 3 over 3 is common, and then we remain with natural log of x minus 1 over 3. Okay, so plus c, of course. You can add a c at the end, plus c. So that's the integral for that. Okay, let's look at more advanced questions. Okay, so we'll be progressing step by step to more advanced questions. Let's look at this one just before we proceed to the more complicated ones. So it looks simple, right? What's the integral of natural log of x? We know the derivative is just 1 over x. Now, what's the integral? So we use integration by parts as well. So in this case, we take it as a product with 1, or we can just put dx. Okay, we're integrating it in respect to dx. So obviously in this case, our u is definitely going to be equal to the natural log of x itself, right? And then our dv is just going to be dx. So putting dx as your dv is as good as just having a 1. Okay, others will take it as though it's a product of 1 and natural log of x, still the same. Okay, so u is equal to natural log of x. What's the derivative? So we know the derivative of natural log of x is 1 over x. dv, what's the integral of 1? It becomes x, because yeah, it becomes x. That's direct, straightforward, because the derivative of x is 1. So we can now substitute. What is our u? We're following this. So our u is natural log of x. What's our v? Our v is x minus, what's our v again? It's x. What's our du? 1 over x. So we have x natural log of x minus, so we have a product between our v and our du, which will just now give us like a 1, right? So we have x natural log of x. What's the integral of 1? It's x, so plus c. So that's our derivative. Sorry, that's our integral plus c. Okay, so we usually interchange the names. Let's see how we can basically get to determine the integral of e to the power x sine of x. So we integrate this using the integration by parts. The formula for integration by parts is the integral of u dv is equal to the integral of, it's actually equal to uv minus the integral of v du. Okay, so you can actually see that here you've got u dv, and then on the other part you're subtracting the opposite, v du. Okay, so each time you're trying to determine the integral, you need to assign u and dv. Okay, so in this case we'll say let our u basically be equal to e to the power x, and then let our dv be equal to sine of x. So of course I've introduced you to the letters aliate, which helps you assign u, but in this case this is one of the exceptions where you can actually assign u to e to the power x despite it being the last one in most of the cases. Okay, so therefore we have our u being equal to e to the power x. So if that is our u, then it means the other part is dv, which is sine of x, right? So sine of x. Okay, so let's go on and try to determine the other remaining. So if you've got u, you need du. So your du is going to be what? What's the derivative of e to the power x? So you know the derivative of an exponential function, e to the power x, is multiplying by the derivative of the power. So the derivative of x is 1. So if you multiply the entire function by 1, nothing will change. So it's just e to the power x. And then for dv, it means we have to integrate sine of x for us to get v, right? Because dv means the derivative. So what's the integral of sine of x? The integral of sine of x is negative cosine of x. Okay. So let's now substitute. So we have uv. So our u is e to the power x. Our v is negative cosine of x. And then minus the integral of what? V du. So what's our v? Our v is negative cosine of x. And then our du is e to the power x. Okay. So let's move on. Okay. So at this point, negative cosine of x multiplied by e to the power x is going to be, we just put the negative, so that we have negative e to the power x cosine of x. And then this negative and that negative inside, we can put the negative from inside so that we can have a positive. So let's just have a positive. Okay. So we now have the integral of what? We have the integral of ex cosine of x. So you see that we still need to look at this integral again. We have to integrate it. So we can do the same. We have to use the same method, integration by parts. So let our u be equal to that, and then let our dv be equal to that. So we're applying the same equation that's here. Okay. So what happens at this point? So our u, as you've seen, is maintained. Now our dv has to change to cosine of x. So our dv is now cosine of x. So we'd have to determine the value of v. So what's the integral of cosine of x? It's sine of x. So if you're confused about the integrals and derivatives of trigonometric functions, check the link in the description for a video about that so that you're easily able to remember. Okay, we can now substitute. So we have negative e to the power x cosine of x plus, so the first part is uv. So what's our u? Our u is e to the power x. What's our v? Sine of x minus, so we have this part again, the integral of v du. So our v is sine of x, our du is e to the power x. Okay. So let's move. So we have negative e to the power x cosine of x plus e to the power x sine of x minus e to the power x sine of x. So I've just moved this one the other side. Now if you try to check what we have at this point, you'll notice that the question that we're trying to find is basically what we've got obtained on the other end. So us taking a step to integrate this again is like we're just repeating. It's like we're now getting into an endless loop. Okay, so what do? So since these are like terms, we can correct them on one side, right? So this negative, so we'd have to add the additive inverse on both sides. So here if you add positive of it, it's going to disappear, right? And then the other side, it's going to end up adding with the other one so that they become 2. So we're going to have 2 of integral of e to the power x sine of x being equal to, so what remains is this part. So I'll start with the positive part, that is e to the power x and then sine of x, minus the negative part, e to the power x cosine of x. Okay. Okay. So now we know that we want to remain with only the integral of v. So we'd have to divide by 2, or in other terms multiply the entire equation by half, right? So if we do so, we're going to remain with the integral of e to the power x sine of x is equal to e to the power, now this is now multiplied by half, so we now have half, and then e to the power x sine of x minus e to the power x cosine of x. Okay, so we can still go a further step by factorizing e to the power x, which is also common, so that we can just remain with sine of x minus cosine of x. Okay, so this is basically how you get to integrate this. So of course, not forgetting we have to add plus c every time we integrate. So how do we basically get to integrate the integral of e to the power x and then cosine of x? Okay, so this, as you can see, you can't use integration by substitution. So integration by parts is the method we're going to use because we can't use partial fractions as well. So as we know, the formula is the integral of u dv is equal to uv minus the integral of v du. Okay, so if you look at u, in this case our u will be that, our dv will be that. Okay, so let's write that down. So we have our u being equal to e to the power x. So since that is our u, the derivative of u is going to be, derivative of e to the power x is just e to the power x because we are multiplying by the derivative of the power. If you are new to differentiation of exponentials, check in the link, check for the link in the description for that. And then we have dv now, which is cosine of x. So if our dv is equal to cosine of x, it means the integral of our dv, which is going to be v, is going to be what? Sine of x. Okay, so we can go on and substitute. So we're going to have uv, we have e to the power x, our v is sine of x, and then minus the integral of v du, so our v is sine of x, and then our du is e to the power x. Okay, so I can write this just on that stage. So we've got this. I prefer starting with the exponential part, right? So we can have e to the power x and then sine of x. Okay, so you will now notice that this part already requires also integration by what? By parts, right? So in that case, this is still going to be our u, and then that is going to be our dv. So we can substitute. So you can see that only dv has changed, so our u still remains the same. So for our dv, we now have sine of x. So what's the integral of sine of x? It's going to be negative cosine of x. If you are new to how to go about that, dealing with the derivatives of trigonometric functions, check for a video. The link is in the description. Okay, so we can go on and substitute this same equation. So let me just move it a bit this side. So we have the integral of e to the power x cosine of x being equal to e to the power x sine of x. Okay, so we have a minus there. So what's going to be, what's coming out as a result? So we have first of all uv. So for our u, we have e to the power x, and then multiplying by negative cosine of x. So it's just going to be negative cosine of x. And then what else? Then we have this part minus the integral of v du. So our v is negative cosine of x. Okay, and then du, v du. So our du is e to the power x. Okay, let's simplify this before we go any further. So we have e to the power x sine of x, and then minus, so in the brackets, let's distribute this negative already. So this negative multiplied by this other one inside becomes positive, so I have positive e to the power x cosine of x, and then this negative and that negative as well will give us a positive, so I have a positive integral of what? So inside there we have it, so it's still a negative, by the way, it's still a negative, so I have a negative of e to the power x cosine of x. Okay, and then on the left hand side we have the integral of e to the power x cosine of x. So you can see what we have, right? Now you can see that this is now almost like the same with what is on the other side, right? Because we know that if you've got a negative inside there, you can pull it out so that it comes out, so that you have that. So this is equal to that. Okay, so if we are to integrate this again, we're also falling into a loop. So let's correct them on one side. So we're going to have 2 if it goes the other side, or we add the additive inverse on both sides. So on this side it's going to subtract, and then we end up coming up with a 2 on the other side. E to the power x cosine of x is equal to e to the power x sine of x plus e to the power x cosine of x. Okay, so let's multiply now by 2, right? By half, sorry. Let's multiply by half on both sides. So the entire equation multiplied by half. So we're going to end up with this part 1 over 2, and then we have, you can also factor out the e to the power x, which is also common. So let's say half e to the power x, and then in the brackets we can have sine of x remaining plus cosine of x. So this part and this part, this has been factorized, and then we multiply by half, that 2 has disappeared. Okay, so this is basically this is what you should expect as a solution. Of course, not forgetting plus c each time you basically get to integrate. So how do you integrate x squared e to the power 3x? Okay, so let's talk about integration by partial fractions. So before you actually get to look at integration by partial fractions, it's important to understand what partial fractions are. So I'll actually embed that in this lesson. Okay, so some of the few things that we need to know is that if you look at the integral of 1 over x dx, what you should expect is the integral of that is going to be the natural log of the moduli of x plus c. Okay, so equally when you're talking about 1 over x plus 1, you expect the same. The integral there is going to be the natural log of x plus 1, and then of course plus c. Very, very important. So in a case where you have maybe a 2 there, you have to have a 2 there. I'll explain how. Okay, so you're able to pull out the 2 from this part, you're able to pull out the constant, so that you can have like your 2, and then you remain with your 1 over x plus 1, and then you integrate, okay, to give you that. Okay, now more specifically in this video we're going to focus on integrating fractions. 2x plus 1, for example, divided by x plus 2, okay, divided by x plus 1, x minus 1. So how do you integrate that? How do you integrate this? So I actually have up to about 6 questions that we're going to look at, so stick around. One more thing that you need to know is determining the integral of x minus 1 to the power 2 dx. This is very important because we're going to have this one part of being part of the results of a partial fraction. So from that point, that's where we're going to apply this and also what I'm from explaining. The basic idea that you need to have is when you look at a fraction like 2x plus 1 and then over x plus 2 and then x minus 1. So you, before you basically get to integrate this, you need to split it into its partial fractions. And so if you split it into partial fractions, you may have something like 2 over x minus 3 and then minus 1 over 2x plus 1. So don't worry, I'm going to explain how you go about this. So now, when you have reached this point, you can now distribute the integral separately. Okay? This is now why it's important to understand. So you can pull out the 2 there, and then you end up with natural log of the moduli of x minus 3. For the other part as well, natural log, and then the moduli of what? 2x plus 1, and then plus c. So I'm going to explain on how you move from this stage to this form. Okay? Now, at times, instead of having that, you may have that result. So how do you do it? So you only actually introduce the natural log when you have a power over 1. Okay? So if you have a power of 2 going up, you use integration by substitution at that point after you've split into its partial fractions. So what you might expect there is let your u be equal to x minus 1. Okay? And then differentiate that in respect to x. So you end up with du dx being equal to just 1, right? That's equal to 1. So your goal obviously is to make your dx a subject, right? So at this point, if you cross multiply, just be du is equal to dx, right? Okay? It makes more, there's a bit of a difference when you have, let's say, x squared, because that is now going to involve you having like x, sorry, 2x in that case. So you end up with a 2x, right? Okay. So at that point, you're going to have du dx being equal to 2x. And then if you try to make dx a subject, you end up with du over 2x is equal to dx. Okay. So therefore, I have the integral of 1 over, now remember what is in the brackets here is equal to u. So I have u now squared, and then your dx is now du over 2x, right? Okay. So at this point now we want to integrate this. So how do you basically get to integrate it? So when it comes to integration there, what you need to expect is you're going to look at this one, take it on top, and then you have u to the power negative 2, right? And then of course do the same. What are you going to do? You're going to add a 1, divide by the result, which is of course negative 2 plus 1 is going to give you negative 1. So and this disappears at that very point. So you end up with something like u to the power negative 1 divided by negative 1, so it's that. And then your u, of course, you know it's x squared minus 1. So you have a negative outside, and this is equal to the power negative 1. So having a power of a negative 1, and then of course, don't forget we are now dividing by the 2x there, right? So over 2x, and then of course dx, du. So the du would disappear since at this point we've already integrated. We can add a constant c, and then you can have it as a positive by taking it to the denominator, so that you end up with something like negative 1 over x squared minus 1 to the power 1, and then 2x, and then you have like plus c. This is how we basically get to integrate that by substitution, and that will be very, very useful as we look at integration by partial fractions in detail. Okay, so we'll start with a basic one. So how do you basically get to integrate 2x plus 1 over x plus 2 x minus 1? So before we basically get to integrate this, we need to split it into its partial fractions. So let's have 2x plus 1 as our fraction over x plus 2, x minus 1. So how basically do you get to split this into its partial fraction? So how do you basically take this into its partial fractions? So it's very basic. So look at what we have in the denominator. So we're going to have two different denominators, x plus 2 and then x minus 1, and then we just add, and then of course we just put our letters of choice on top. So I have a there and b there to represent that. Okay, so we'll take it as though we are solving on the right, and then what do we get to have? Let's have a common denominator, so we end up multiplying them again. Okay, so divide this into what we have. The result will be x minus 1. So end up a multiplying by x minus 1, and then for that part, if you divide that, what remains is this part. So you end up having b multiplying by x plus 2. So don't forget we have 2x plus 1 and then over x plus 2 and then x minus 1. So at this point what we're saying is the denominators are equal, so we can equate the numerators, right? So for the numerator, what do we have? So we have 2x plus 1 being equal to, so let's just actually get to distribute. So a times x, it's ax minus a. For the other part, it's bx plus 2b. Okay, so what do we have? So let me correct the like term. So I have ax plus bx, and then we have 2b minus a, and then this other side what you have is 2x plus 1. So we need to find the values of a and b. So I can easily substitute, or I can easily factor out the x there. So if we do factor out the x, what do we have? So we have a plus b, and then x is common, right? Okay, equal to 2x plus 1. So at this point, if whatever we have is true, then the part having 2x should be equal to the part having x there as well. So we now have 2 being equal to a plus b, and then this constant that we have 1 should also be equated to the parts that are not having any x on the other side. So 1 is also equal to 2b minus a. Okay, so I can now use basically take them to be simultaneous equations. So I can make my a to be the subject in this formula. So we end up with 2 minus b equal to a, and then I can substitute in the other equation 2b minus the a. So for the a we have 2 minus b, and then our 1 is equal to 2b minus 2 plus b. 2 comes the other side, we have 1 plus 2 equal to 3b, and then our b essentially becomes 1, and then if our b becomes 1, we have now 2 minus 1 being equal to a. A is also, a becomes what? We're finding a to be 1 as well. Okay, so here we made a the subject, we had 2 minus b, and then from that point we went to this other equation where our 1 was equal to 2b minus a, and then we had to substitute where we had our a, we put 2 minus b. Okay, and then 2b plus b gave us 3b, this gave us 3. Okay, so this is basically what we have. A equal to 1, b equal to 1. So you might want to prove if it's true. So you have a common denominator, x plus 2, x minus 1. So if you divide, you're going to have x minus 1 for the first part. Multiplying by 1 will just be that. And then as well, there x minus 1 give you x plus 2. Multiplied by 1, it will just be itself. Right? So if you basically get to add them, x minus 1, x plus x, they are going to have 2x. And then negative 1 plus 2 is just going to be a 1, which is actually now equals what we have on the left hand side. So now that we've seen what it basically gives us after performing or splitting it into partial fractions, we have 1 over x. So we have 1 over x plus 2, and then 1 over x minus 1. Okay, so this is what we have. So we can distribute the integral now. So when you distribute the integral, what do we have? So since they're all raised to the power 1s, it's going to be direct. So we're just going to have the natural log of the moduli of x plus 2 plus the natural log of the moduli of x minus 1, and then plus a constant c. So that's the integral. So I think what's the most important is knowing how to handle partial fractions, and basically getting to perform the integration on the partial fractions is very easy, as you can actually tell from this example. So let's look at another one. Let's say we have the integral of 3, and then you have x plus 1. How do you basically go about it? Let's determine the partial fractions of 3 over x plus 1. Okay, so here we've got two factors, which are x and x plus 1, making up the common denominator. Okay, so we can have letters a and b represent the numerators, and then find the values of a and b. So look at the right hand side. We can come up with a common denominator, which will give us again x and then x plus 1. Just multiply the denominators we have, and then after you divide by x, what remains is the other part, x plus 1. So you have a multiplying by x plus 1, and then the other part you have b multiplying by x, right? So now our goal is to find the values of a and b. So remember, this is equal to that, right? The denominators are the same, so we need to equate the numerators. So we have 3 being equal to ax plus 1, or I can actually go direct by multiplying what we have. So a multiplied by that, we have ax plus a, and then we just have our bx. So we have 3 being equal to ax, and then plus bx, and then plus our a, right? So in this case it becomes easy, because what we basically have is the fact that our a is the only constant, okay? And then this side we only have 3 as a constant. So directly we can see that our a is equal to 3. Now for this part, we don't have any part attached to x, so we can introduce a 0x there. Okay, so if that's the case, then we expect that a plus b, of course after you factor it out, if you factor a plus b, you factor out x, sorry, you remain with a plus b. So the a plus b should be equal to the 0, right? So a plus b should be equal to 0 because they are the ones attached to x. So now our a is already what? Our a is 3. So therefore our b is going to be what? Negative 3. Okay, so we found the values of a and b. So our a is 3. So 3 over x, and then our b is negative 3, and then over x plus 1. So that's basically how we determine the partial fractions here. So what we have is we have our 3 over x, and then minus 3 over x plus 1 as our partial fractions, as you can tell. So at this point, we distribute the integral as well. So first step, let's pull out the constants. So our 3 there, and then we remain with 1 over x, and then there we pull out our 3, and then we have 1 over x plus 1. So what do we expect? So we have 3 natural log of x minus 3 natural log of the moduli of x plus 1 plus c. I'll emphasize, we only basically get to do this when the powers are just ones. Okay. Okay, let's look at another one. How do you basically get to perform the integration on a question like 1 over x minus 1 squared and then x plus 1? So we basically call this repeated factors, where in a case where you have so at this point we've already performed integration by other means, so we're going to learn how to perform integration by Trig-Substitution. So there's this common one that you know, the identity under trigonometry: sine squared of theta plus cosine squared of theta is equal to 1. This is going to be very, very important. So we're going to integrate a case where we have the root of 9x squared minus 4 divided by x. Okay, so I've got two more other questions having different forms. For example, I also have 1 over x to the power 4, the root of 9x squared. Okay, so we need to integrate this one. I also have a third one that you're going to see later on in the video. Okay, so basically this one requires us to integrate it, of course, in respect to x, and then you notice that substitution here can't work. You notice that you can't use partial fractions, you can't use integration by parts. So the only way you can integrate such a question is by Trig-Substitution. Okay, so let's get back to this identity that you already know. There are a few things that I want you to recall. Okay, so one of the most important forms of this identity that I would want you to know is a case where you divide by cosine squared of x, right? So let's divide the entire equation by cosine squared of theta. Cosine squared of theta, cosine squared of theta. So you already know that if you divide sine by cosine squared, you get tan squared of theta. Cosine by cosine is 1, and then 1 over cosine squared of theta is secant squared of theta. This is going to be very important. So you can also write it in another way, where the 1 is on the other end, right? So number 2, so if you can have the 1 to be on the other end, what we're going to have is tan squared of theta being equal to secant squared of theta minus 1, which I can just, so now let me move the tan squared theta to the other side. Still the same, right? So these two forms of equation are going to be very, very important. And then the third one, which is also very important, is a case where the same sine squared theta plus cosine squared theta, which is equal to 1, I can also decide to make cosine squared theta a subject, right? So this one can just be on the other side. So the third form, which is very important, is sine squared of theta being, so actually making cosine squared of theta a subject. So if you make cosine squared of theta a subject, you're going to have on the other side 1 minus sine squared of theta being equal to cosine squared of theta. So these ones are the ones that are going to be determining, these ones are going to help us determine what we are going to substitute, right? Okay, so let me take you back to the first question we are going to look at. The integral of the root of 9x squared minus 4 over x. So observe what is under the brackets, or what is under the root there. So if you look at 9x squared minus 4, What do you think? Which one is it more like? Remember, there's a negative first of all. So which one is it like? Pay attention, the x squared is representing these parts. Alright? So basically it's appearing more like this one because it's a negative and then you are starting with a square. So for such a question, you're going to substitute sec theta. I'll show you how. And then in a case where for example, if we had the same question being 4 minus 9x squared and then a square root, this one, the x squared is on the negative part. So which one is that? So that one would involve us substituting sign. And then in a case where you have an addition, you would have to use the first one. This is very, very important, and each time we are dealing with trig substitution. Alright? Okay, so now let's integrate this question using trigonometric substitution. So the other thing that you need to know under the integration by trig substitution is know the basic derivatives, okay? So one thing that you need to know, for example, is that the derivative of secant of x is going to be secant of x tangent of x, okay? Very important. So if you are new to this, watch a video, the link is in the description, where you learn how to determine derivatives of trigonometric functions. Okay, so let's basically get into it already. So one thing that I already mentioned is if you look at 9x squared minus 4, you notice that this is in the form of secant, right? Because you know that secant square of theta minus 1 is equal to tangent square of theta. So I've already explained that this helps you determine what you're going to substitute. Okay, so we have a squared starting and then minus a 1. So this is appearing more like this. So we are therefore going to substitute the secant. Okay, so now where are we exactly substituting? So one thing that you need to understand is each time you have this form of, if you look at the square root there, we have 9x squared minus 4, right? So whenever you have that form, I can actually write it in this form because we have b squared, okay? So b squared x squared minus a squared. So whenever you have got that form where you are starting with x squared attached to a b which is squared, we substitute the value of x by a over b and then secant theta. Very important. Okay, so I can also mention beforehand to say if we add a different one, a square root of, let's say, something in the form of a squared and then minus b squared x squared. Now you know that in the case where x squared is of course representing the trigonometric function, the one that can basically represent this one in a better form is 1 minus sine squared of theta. Okay, so this is the one that represents this one in the better form, right? So this means, of course, we know this is of course equal to cosine squared of theta. Now it means we're going to substitute the sine theta. Now for such a one, the value of x is going to be in the form of that. So writing it in this form, it is still going to be a over b, but instead of secant theta, what are we going to put? We're going to put sine theta. Okay, that's very important for you to take note of. Now let's get back here. So each time we have something in the form of b squared x squared minus a squared, we are always going to substitute this. Okay, now we understand that b is always going to be the part that is attached to the value of x. Alright, and then a is going to be the part that is isolated from x. Okay, so you notice that these ones are expressed all in the form of a square. So let's try to express what we have in the form of a square. So we have the root of, so 9 can be expressed as 3 squared and then x squared and then minus 2 squared for our 4. So we can now see that our value of x in this case is going to be our a, which is isolated from x, is 2 over our b attached to x, which is 3, and then we have secant of theta. So what is our value of x in this case? Okay, take note of that. So we can now try to substitute in the equation we have. Now just before we get to substitute, I would want us to simplify it a bit. Okay, I would want us to simplify the square root. So let's try to substitute what we have. So you can see that in the square root there we are substituting x squared. Now we just have x. Okay, so what happens if you square this? So if you square it, what happens? 2 to the power 2 is going to give us what? 4. 3 to the power 2 is going to be 9. Second squared is going to be secant squared theta. Okay, as simple as that is. So now we know that is x squared. Now let's substitute. So we are putting that where there is x. So we have 9. So where there is x, we have 4 over 9 secant square of theta, and then we have a minus 4. Don't forget we have got a square root. So square root, and then of course we are dividing by our value of x, right? So we're dividing by x. So x itself was just 2 over 3 secant squared of theta. Okay, so that's the point where we've reached now. So we've already taken note of this. I can remove it. Even this, we've already taken note of it. Don't forget the value of x, right? Don't forget what we've said about x. X is 2 over 3 secant of theta. Okay, so let's now try to simplify what we have, of course, at this point. So don't forget this is a division. We can remove this line. So we can basically try to simplify what we have on top there. So we have 9 multiplied by 4 over 9 secant square of theta. So the 9 basically can divide there, and then remain with 4 secant square of theta. So we have the root of 4 secant square of theta minus a 4, and then divided by 2 over 3 secant of theta. So by the way, you can always be moving with the integral. We're trying to determine the integral in respect to dx. Let's not forget that. And let me draw a line here so we can have other space on the other side. So let's move on to the next step. So under the square root there we can factor out the 4. So that you have a 4, and then you remain with secant squared of theta minus a 1, and then the square root. So the square root there can be split. You can have root of 4 and then root of this other part. Okay, just wanted you to have a picture of that. So over 2 over 3 secant of theta. So isolating the square root there, if we separate the square root of 4 and the square root of this part, the square root of 4 is going to be a 2, so we can have a 2 outside. I believe we've done that, and then we're going to remain with secant square of theta minus a 1 under the brackets. Now you know that secant square of theta minus a 1 is something that I mentioned earlier on when we started. So that is an identity which is equal to tan square of theta. So I'm going to substitute that on the next stage. And then we have over 2 over 3 secant of theta. So we're still simplifying. We've not yet started determining the integral. Can get back to this side. So we can have 2 now, 2, and then secant square of theta minus a 1, I've said that's an identity. So that is basically equal to tan square of theta. So we have root of tan square of theta. Okay, and then we are dividing by 2 fade of secant theta, right? So 2 fade secant of theta. So if you bring back our integral, we're integrating this in respect to what? In respect to dx. Now what is the root of tan square of theta? So that's going to be the moduli of tan square of theta. Now in this case, since we're dealing with an indefinite integral, we can just take it to just be a positive result. So we have 2, and then of course the moduli of tan theta, we just take it as a positive value, so that we just have 2 tan theta, and then of course we are dividing by 2 fade of secant of theta, right? Okay, so after reaching this point now, we can do away with the dx, since we just want to remain with theta. So let's deal away with a dx there, so that we can easily now integrate. So that's after you've dealt away with the square root. I suggest you do that. So our x value is equal to this. So our dx, the derivative of x, what's the derivative of secant? It's something that I mentioned. Okay. So the derivative of secant is basically secant of theta tangent of theta. Now we have, of course, a coefficient there, so it's going to be 2 over 3 secant of theta tangent of theta. That's the derivative in respect to what? To the theta. Okay, so that's our dx. So we can now substitute that. We can now substitute this, move it a bit down. So we're going to have the integral of, so we have 2 tan theta over 2 over 3 secant of theta, and then now whatever is dx, we put this. So we have 2 over 3 secant of theta tangent of theta, and then we now have the theta there. Okay, so we can see that secant of theta can basically divide by secant of theta, right? And then tangent of theta can multiply by tangent of theta. So we have the integral of, so we start with a 2 there, so 2, and then tangent by tangent is going to be tangent square of theta, and then we are dividing by, first of all, before dividing, we have this 2 over 3 that I shouldn't forget about, so I'm multiplying by 2 over 3, and then we're also dividing by 2 over 3. So dividing by 2 over 3 is as good as multiplying by its reciprocal, which is going to be 3 over 2, and then of course the theta at the end. At this point, what we have, so we have the integral of, so we can cancel some of these things, so that and this can divide, right? And then we're just remaining with the 2 there. So the 2 which is remaining as the only constant can be pulled out of the integral, and then we just remain with the integral of tan squared theta, right, in respect to the theta. So at this point it has become more simplified. Okay, so we're trying to determine the integral of this. So it's going to be a bit cumbersome to determine the integral of tan squared of theta. So you can basically just put back the identity, which is going to be more easier. Okay, so you know that tan squared of theta is equal to what? From that identity that I gave you at the start. So you notice that it's basically equal to secant squared of theta minus a 1. Okay, so don't forget that identity is going to be very useful. You don't have to master all these things, because you know sine square of theta plus cosine square of theta is equal to 1. So if you divide by cosine square of theta, you're going to get this identity. Okay, so at that point you are easily able to integrate. Okay, you're easily able to integrate. So what's the integral of secant square of theta? What's the integral of secant square of theta? So we're going to have 2, and then the integral of secant square of theta is just tan theta, and then the integral of negative 1 is just going to be minus theta, and then because we're integrating in respect to theta, of course, and then plus a constant c. So this is our answer in terms of theta. Now if we go back to the question that we started with, the question was given in terms of x, so they obviously want us to find an answer in terms of x, right? So how do we basically do that? So it's very easy. At this point, the complicated work has been done. Just with practice, this will be very easy for you to handle. So we'll use trigonometry again. We'll use trigonometry I hope you've not forgotten what we started with. We said let our x be equal to 2 over 3 secant of what? Secant of theta. So let's make secant of theta the subject. So that would mean that we need to multiply both sides by 3 over 2. So we're going to have 3x over 2 being equal to secant of theta. So from there, we're able to come up with a triangle. Okay. Now what do we know about secant of theta? So we know that secant of theta is the same as 1 over cosine of theta. Okay. So in short, secant of theta is the reciprocal of cosine. Now we know that from SOHCAHTOA, when you look at the part for cosine, the trig ratios for cosine is cosine of theta is equal to adjacent over hypotenuse. Now in this case, where we're dealing with secant of theta, it's the reciprocal of cosine. So therefore it's going to be the opposite. It's going to be hypotenuse over adjacent. So secant of theta therefore is hypotenuse is going to be on top, since it's a reciprocal of cosine. So meaning that the 3x is the hypotenuse and then the adjacent is the 2. So we can draw that triangle. Okay, so taking this part to be our theta, the adjacent is 2 then, and then the hypotenuse along the side is 3x. So we can find the opposite. So from Pythagoras theorem, we know that it's going to be the difference, the square root of the difference of the square of the hypotenuse minus the other adjacent side. So it's going to be the square root of 9x squared minus 4. That's from Pythagoras theorem. So we've come up with a triangle. We should be able now to find the values of this, right? So what's tan theta from that triangle? So tan theta, we know that from SOHCAHTOA, tan is opposite over adjacent, so the opposite is root of 9x squared minus 4. So 9x squared over the adjacent side is a 2. Okay, that's tan theta. We can also find theta. So since we're dealing with secant here, I would prefer going for cosine inverse, but you can use any, there's no restriction by the way. So I know that cosine of theta is adjacent over hypotenuse. Adjacent is 2, hypotenuse is root of that, right? So the hypotenuse is 3x. So we can try to make theta the subject by, it's going to be arc of that, right? Which is just cosine inverse. So cosine inverse of 2 over 3x. That's the value of our theta. And then we can just now substitute. So our answer in terms of x is going to be 2. So for tan theta, it's equal to that. So it's going to be the root of 9x squared minus 4 over 2. And then, of course, this is in brackets. And then minus what? Minus theta, which is just cosine inverse of 2 over 3x. And then in brackets plus a constant c. Okay, we can end there as our solution. If you want, you can distribute these two. And if you do, this and this will divide, and then you end up with a 2 there as your answer. Okay, so in that form, the final result becomes the root of 9x squared minus 4 minus 2 arc cosine or cosine inverse of 2 over 3x plus c. So this is how you basically work with the integration by trig substitution. Okay, so let's look at another form. So we'll look at the application of integration. So this is to deal with first of all the area, and then in the next story we'll look at where we deal with volume of solids, rotations and all, but we'll focus under the area. So I've got a number of questions that I would want us to look at to just understand the concept. But one thing that is very important is we've already looked at definite integrals where we have the upper and the lower limits. So that's the application, that's what we're going to focus on. Taking this function to be f of x. So if you have a and b as the points where it is cutting the x-axis, so if you want to find this entire area under the curve, or in other terms, any area bounded between a curve and the x-axis can be determined as the integral of that function and then using the limits, okay, of the points that you're interested in. So if you want to find the entire area from a to b, then you would have to use a and b as the limits. Now if you are interested only in a small part of this curve, let's say from that point to that point, so if the limits are x and y respectively, then that would mean that your integral is going to be dependent on those limits y and x for the function f of x. That's a basic idea. So the area bounded between the curve and the x-axis can be found as the integral of a function using the limits of the x values that you're looking at the values of x that you're interested in. What values of x, what area between what values of x are you interested in? So this is not only restricted to a part where you have such a curve. Sometimes you may also have a curve, so interestingly placed, where it is having a minimum like that. So even in such a curve, all the same, if you want to find the area bounded between the x-axis and the curve, just have to get the limits that you're interested in. So if you want from that end, then you'd have to draw all the way down and get the limits as well. But all the same, what you're going to calculate if you integrate the function, if this is g of x, if you integrate the function and then of course applying the definite integral, but as you look at the limits b and a, what you're going to get is the area bounded by the curve and the x-axis. That's the idea behind that. Okay, so even if you have a function below the x-axis, if you integrate it, apply the limits, you still notice that the area is going to be the area between the x-axis and the curve. Now in such a case you add a negative, because since it is below the x-axis, the y value is negative, so you're going to get a negative value. So add the negative so that you can get a positive area. Okay, now some of these questions are made to be more interesting. They can't just ask you to find the area and all that. They may actually include things like for example, if I go back to the previous page, you'll notice that they can, looking at the first curve, you may have a line or a linear function cutting like that, and then they shade a certain region, let's say this region. Okay, so let me just erase that part. Yes, so they ask you to find the area bounded between the line and the curve, this region. What did you do? So what you can do is, first of all, find the area between the curve, which is higher, okay, by looking at the limits that you're looking at. So if you look at those points where they're intersecting, and then let's take it, they're intersecting at a and b, so the x values of b and a will be used. So for the function itself, f of x, and then we'll subtract the area below the linear function. So if the linear function is g of x, we'll say the integral of g of x, and then you also look at the same limits b and a. What you're going to get is the area between the curve and the linear function. Now let's try to see, we have such a question like that one, but let's look at this one where we want to find the area below the curve. What do we need to do in such a case? So certain things are not going to be mentioned. For example, 0 may not even be indicated, but you need to know that since it's cutting at a point of intersection between the y and the x-axis, you know that it's cutting at 0. So meaning that you already have your limits. So for us to find the area all we just have to do is just apply integration. So the integral, the limits that we have in this case, we have 2 and 0 respectively, and then the function is x squared minus 2x for that curve. So we are interested in finding the area between the curve from 0 to 2. Now in some cases you may be only interested in, let's say, halfway, maybe up to a 1 there. Then in such a case you use 0 and 1 as your limits. So the point I'm trying to make is it's not always that they will be interested in the entire region. So in this case, let's reintegrate the function that we have. So what is the integral of x squared? So the integral of x squared is going to be increase the power by 1, divide by the result, and then minus 2x, again increase the power by 1 divided by the result. And then of course you understand plus c, but we are dealing with definite integrals, that is not necessary. So we have a 2 and a 0. So we've already talked about definite integrals, so I believe this shouldn't be a struggle for you to handle. But of course we need to add the negative since it is below the x-axis for our result. Okay, so what do we expect? So in terms of simplifying that, we're going to have negative of that, and then since we've already integrated, we'll get the first part, we'll plug in a 2 to the power 3 over 3 minus. So of course at this point, to make things easy, that can divide. So we only have x squared, so 2 squared, and then minus the lower limit now where you have a 0, so 0 to the power 3. So you already know that is going to give you a 0, and then 0 to the power 2. So the other bracket, since everything is attached to an x, it will be eliminated as a 0, and then of course 2 to the power 3 gives us 8, so 8 over 3 minus 4. So I believe that is going to be 3 times 4, 12, 8 minus 12 is negative 4, if I'm not mistaken, negative 4 over 3, and then the answer becomes 4 over 3. Now the units for area is what? So units squared. Okay, so apply that very concept to this question. I already explained how you can handle it. So if you're trying to find the area bounded by these two curves, one thing that you know is the one that is on top, you're able to find the area all the way up to the x-axis, and then even for the one that is below, you're able to find its area all the way up to the x-axis. So all you have to do is subtract them. So the basic idea is, if you look at this area for this curve, and then you come and look at the area for the other one, so they are all reaching the x-axis. So if you want to get the area between them, all you have to remove is remove the blue lines from the green lines. What remains is that region between them. So let's start with a bigger one, the one that is on top. So the integral of, so the limits, we've got 3 and of course 0, since they are meeting at the y-axis. So 3 and 0 as our limit. So in such a case where we've given you both functions, even if they don't give you the points where the curves are cutting, you can just equate them. Equating them will tell you are going to get the values of x where the functions are equal, because at the point where two functions meet, at that point they are said to be equal. So you can find those points where they cut or meet by equating them. Okay, so in this case we're going to have the upper one is negative x squared plus x plus 6, and then minus the lower one, which is 3, 0 as well. The function is x squared minus 5x plus 6. So everything else is not complicated for you to handle. All you just have to do is integrate the functions. Okay, so if you integrate the first function, what are you going to have? So we understand that you need to increase what? You need to increase the power by 1 and all. So let's try to basically just do that. So if you increase the power by 1, you're going to have negative x to the power 3, and then over 3, and then the x as well, increase the power by 1, it becomes 2, and then divide by 2, and then plus. If you integrate 6x, it's like you have a 0 there, so it will become 6x divided by the 1. So don't forget the limits that we have, 3 and 0, and then minus the other part. So for the other part, what's the integral there? Increase the power by 1, so it will be the power 3, divide by that again, and then plus 6x. So the beauty about this is if you look at them, are you able to see any part that is like common, or that you can cancel out? Any part that is common. So for me, I can see that 6x is common, so I feel there is no point of leaving it there. So 6x, since they are of the same signs, after subtracting, because of a minus, they can just be divided, they can just subtract, so that you stand out with just the other parts. Okay. So at this point, I feel the concept has been gotten, but we can still simplify. So for the first part, we need to plug in 3 first of all. That is for the left part. So we plug in 3, so we're going to have negative, plug in 3 to the power 3 over 3 plus again 3 to the power 2 over 2. Okay, and then this is for the upper limit minus the lower limit. So the lower limit is 0. So you know that for integrals, for any information, when the lower limit is a 0, if you plug in a 0, since you've integrated, that means every part has got x. It is not necessary for you to simplify that, because it is going to eliminate every part of it. Okay, so meaning that in short you just have minus 0. But in a case if you had a different limit, for example a 1, that would mean you'd have to substitute again, so that you can have negative 1 to the power 3 over 3 plus so. So in this case it's just minus 0, which is not necessary. And then we'll now focus on the other part. For the other part, we have x to the power 3 as well, so we'll put 3 to the power 3, since that is the upper limit, minus 5, 3 to the power 2 over 2. Again, the limit is still the same, so the 0 is also not necessary for us to subtract. And at this point, we can now simplify everything. So here one of the 3's can cancel out, so that you remain with 2 of them, and then of course that is going to give us negative 9 plus 3 squared is 9, so we have 9 over 2. Then from the other brackets we're going to have 3 to the power 3, again they can cancel, so that you 1 9 will stand out, and then plus, what do we have? 5, 3 to the power 2 is 9, so 9 times 5 is 45, so we have minus 45 over a 2. I think that is basic mathematics now. So 2 times negative 9 there, that's my way of dealing fractions, is negative 18 plus 9 is negative 9. So negative 9 over 2. And then the other part, we have a minus. So 2 times 9 is 18. 18 minus 45, which is negative 27 over 2. And then, since we've got the same base, negative times negative gives us a positive. Now 27 minus 9 is 18. So we have 18 over a 2, which just gives us a 9. So with a lot of experience, looking at this other one shouldn't intimidate you. So here we want to find the area bounded between the the curve and the x-axis, this area, and then of course what trigonometric function is this one? So this is negative sine of x. So we want to find the area bounded between the curve and then the x-axis. How do we handle it? So for between, of course, negative pi and pi, so we can divide this into two parts, the part between negative pi and 0 and then plus this other part. So we can say the area for the first part, which is from the upper limit is 0 and then you've got negative pi, of course, of a function negative sine x, and then plus the other region. Now since it's below the x-axis, we'd have to add a negative of the integral of, from the upper limit is pi and then you have a 0 and then of course negative sine of x. So obviously you know that how do we integrate the negative of sine? So pull out the negative. So the integral of sine of x is what? So integral of sine of x is going to be negative sine negative cosine of x. So if we multiply by the negative that is outside there, it gives us positive cosine of x. So the integral of negative of sine is positive cosine of x. One way that I remember this is I know that if I differentiate sine of x, it gives me cosine of x. So I know that if I as well integrate or differentiate cosine, it gives me negative sine of x. So that tells me that if I'm integrating that, it gives me a positive cosine of x. Okay, so that means now on our next step, what we have sine of, I've gotten positive cosine after integration. So cosine of x, and then the upper limit there is 0, negative pi, and then plus. Now because of the negative there, it can just become like negative. So we have minus again cosine of x. Now the limits here are pi and 0 respectively. At this point we should be able to substitute what we have. So we have 0 there first of all as the upper limit. So we're going to have cosine of 0 minus cosine of negative pi. You can put that in the brackets, and then minus, for the other part, the upper limit is pi. So we're going to have cosine of pi minus cosine of 0. So you should be conversant with trigonometry for you to be able to handle this easily. But if you look at the graph, I believe you're able to see what is going on. So, but again, this graph is sines, it's negative sine, so you can't say you're able to see. But if I draw the graph, if I was to draw the graph for what? For cosine. Cosine behaves in this way. I know it starts on 1 there, so meaning that on the other part it will continue like that. So obviously you know this is your pi over 2, and then this is pi. Okay, and then obviously this is 0, so obviously at this point again it's negative pi over 2. So if it does continue, then at negative pi it will be below, right? So this is negative 1, that is positive 1. So of course if you have calculators, you can still handle it. It's nothing to struggle with there. So cosine of 0 at this point is a 1. So I have a 1 minus cosine of negative pi at that point, it is at negative 1. So negative 1 minus, for the other part, cosine of pi at this point, I think it's the -1, and then cosine of 0 is also a 1, so minus a 1. So we're going to have, for the first part, 1 minus negative of 1 gives us a 2, and then minus, here in the brackets we're going to get -2, so it gives us a 4 as our area, so units squared. Now what happens if you look at this other interesting question? How do you find the area bounded between the linear function and the other curve on top? So here, just like I said, here the points where these are meeting are not stated. Okay, so how do you handle that? So you just equate them. So root of x plus 1 is equal to half of x plus 1, so that you find the points where they're intersecting. But of course this is on the y-axis, so you believe they're intersecting at the point where it's 0, and you can try it out. If you plug in a 0 where there's x, you'll notice that indeed they will be equal. So let's try to assume we don't know anything. Let's try to find the both points where these functions are meeting. So 1 is common on both sides, so you can subtract, so you remain if root of x is equal to half of x. So at this point, what can we do? I can suggest we square both sides, so that the square root can disappear. So square there, square there. So we are going to have x on the other side equal to, if you square there, it's going to be 1 over 4 and then x squared. Okay, at that point we can multiply by 4 throughout if you want, so that we have 4x equal to x squared, and then take them on one side. I can take this one the other side, so that we have 0 is equal to x squared minus 4x, x squared minus 4x. So if we try to factorize that, we're going to have x and then remain with x minus a 4 equal to 0. So we can find the points, values of x. So x is equal to 0, x is equal to positive 4. So just like we guessed, the first one is on the y-axis, so that's x is equal to 0. So these are the limits that we need. So obviously that is at 4, that is at 0. So those are the limits. So how do you find the area bounded by the curve? So pause the video and try this one out. So obviously we expect that the one on top, which is the integral of course the limits 4 and 0, root of x plus 1, and then we need to subtract the area bounded by the linear function and the x-axis. So also 4 and 0 for the linear function, half of x plus a 1. Now for the sake of your practice, I want you to integrate these functions and then subtract their results. So for the first part, when you integrate the root of x plus 1, how do you go about that? Root of x is the same as x to the power 1 over 2. So if you add the 1 there and then divide by the result, 3 over 2, which is as good as multiplying by 2 over 3. So the result would be 2 over 3 and then x raised to the power 3 over 2. And then the integral of the 1 which is attached is just giving, obviously, what are we going to have if you integrate 1? So the integral of 1 is obviously x. Now here, since we are subtracting, okay, anyway, let me try to show it for a sec. So integral of x of 1 is x. Use the same color there. So plus x. 3, 0, minus the other part. The integral of half of x is what? So how do you integrate? Increase the power by 1. So if you increase the power by 1, you become the power 2. If you multiply by the 2, oh sorry, we don't multiply, we divide. So half of x, increase the power by 2 or by 1, so it becomes 2, and then divide by the 2. You're going to have x to the power 2 over 4. So you have x to the power 2 over 4 plus the integral of 1 again is x. The limits there are 4 and 0 respectively. So I don't know where that 3 is coming from, that's a 4. So you can clearly see again that x is common, so since we are subtracting, this can just be eliminated from both ends, and then we can just plug in, and then you know, of course, when the lower limit is 0 there, it is not necessary for us to plug in because it's going to eliminate it. So we'll just focus on the upper limit. So the upper limit for the first part, that means you plug in a 4, you're going to have 2 over 3, and then 4 raised to the power 3 over 2. Okay, that's for the upper limit. Now it's more like we subtract a 0, because if you plug in a 0 there, everything will be eliminated, and then minus the other part. The other part you plug in a 4, so you're going to have 4 squared over a 4, and then of course we're also subtracting a 0 there, because if you plug in a 0, this will also be eliminated for the lower limit. So ultimately that's what remains, and if you try to simplify, plug that on the calculator, the result you're going to get is 4 over 3 units squared. And this is where we end. I hope you now understand how to apply the integration in determining the area below the curve, the area bounded by the curve and the x-axis, and the area bounded by two different functions. Okay, so continue to talk about the application of integration. So now in this video, I want to talk about solids, the volume of a sphere, volume of a cone, or what happens when you rotate a shape about the x-axis or the y-axis. Okay, so to just help you understand what that means is, consider a case where you have a curve, like that. So you may decide to rotate that curve about the x-axis. So when it is rotated 360 degrees, it's like what you might expect is something like it will also form the other side. Maybe to make it more visible, it's like this is what is going to happen. It's like that's where it's going to pass, and that's a kind of a shape that will form after rotation about the x-axis. Okay, so now to find the entire region that is covered, or the volume of the shape that is produced, we can use integration. So the formula that comes, or the formula for determining the volume about the rotation of about the x-axis, is the integral of pi and then y squared. Okay, so meaning that if you have your equation itself being y is equal to, for example, x, it means that for you to integrate that, of course, taking note of the limits, if this is a and then that is b, so b and a, you'd have to now square the y. So if you square the y, it means you square what is on the right. Okay, so it becomes that b a pi, and then of course it becomes x squared. So let's try to look at a certain example. Consider a case where we have that as our x-axis, and then this is the y-axis. So if you have to have half of the circle, say I have half of the circle like that. Okay, yeah, take that. So taking this circle to be centered about, I don't know, I'm failing to draw. Okay, so taking the center to be the origin there. Some of you have done the conic sections and all the circles, or you know that the equation of a circle about the origin is x squared plus y squared equal to the radius squared. So in this case, if the center is the origin, it means from that point to this point is the radius, and then of course towards the negative you can take it to the negative r there. So if you try to make from that equation, you make y the subject, y squared will be equal to r squared minus x squared, and then obviously y will just come out to be the square root of r squared minus x squared. Now we've already established how to find the volume. Let's assume that you rotate the curve about the x-axis. You rotate it. So if you rotate it, the shear part is likely to form is, in other terms, it's like it's going the other side like that. Right? You're rotating it about the x-axis so that it can come out from this other side. So it will be like that. Now don't forget that there will also be that same region in like that. So the shear part is going to form will be like that if it is rotated about the x-axis. If that is the case, then we expect that if we are to find the volume that is formed, so as we find the volume that is formed after the rotation about the x-axis, we apply the same principle. So in this case, we need to look at our what? We need to look at our limits. In this case, the upper limit is r, the lower limit is negative r, because that's the radius, right? So r and then negative of it, and then pi and then y squared. So we have our equation. So feel free to try it out and see what you're going to get as a volume for the shape formed. Okay, so hopefully you've paused the video and just tried this one out because it's actually very interesting. So I've said rotation about the x-axis, you basically get to focus it on y squared. Okay, so therefore if you look at the volume in this case, the upper limit is the radius and negative radius. So if you try to find, we need to find y squared. In this case we've got a y, so if we square both sides to determine y squared, on the right hand side we are going to have r squared and x squared. So therefore we have now the integral of r and negative of it, and then pi and then y squared. So y squared in this case is r squared minus x squared. Okay, we can move, and then we try to, so our goal now at that point is we should be able to integrate what we have. Now what do we have for integration? We have r squared minus x to the power 3. So integration, what do we do for integration? So let's try to integrate that. Can move this part. So r squared minus x squared. So for the x, increase the power by 1, it becomes 3. Divide by that, and then for the r, since we take it as a constant, so it will be like become x, and then because initially it's like we have x to the power 0, so it becomes x just. So therefore what we have is, of course that can be put out as just a constant, pi can be put out as a constant. So what we have is pi, and then we're remaining with what? So after integration we have r squared x minus x to the power 3 over 3, and then the limits are r and negative r respectively. So now at that point we can now plug in. So beginning with the upper limit, so if plug in where there's x, we put r. So we have r squared minus r to the power 3 over 3, and then for the other part we subtract. So r squared again multiplied by negative of r minus the negative r to the power 3 over 3. Okay, so at this point I can utilize some of the space. So don't forget the pi is outside the entire part. So r times r there gives us r to the power 3. So we have pi, and then inside here we'll get r3 to the power 3, and then minus r to the power 3 over 3, and then minus the other part. We are going to have negative r to the power 3, and then minus there negative r to the power 3 will be negative r to the power 3, so it will now give us a positive. So I have positive r over r to the power 3 over 3, and then of course all these are being multiplied by pi. So obviously, since this is a positive, that is a negative. Okay, let's try to move. We see what we're going to get inside there. So we have pi, and then do you have any like terms? R minus r. So in short, let's try to distribute the negatives. So if you distribute this negative, that will become positive, and then that will become negative. So collecting the like terms, r3 and the other positive one, we have 2r to the power 3, and then this one plus the negative of that, it will also give us a 2. So I have minus 2 of that. Okay, so it's like we have like terms now. So this 3 can multiply the other part. So I have pi 3 times 2 gives us 6. So 6r3 minus 2 r3 over 3. So we get pi, and then 6 minus 2 gives us 4. So 4 over 3, and then r to the power 3. So that can be written as 4 over 3 pi r to the power 3. So I believe that formula is familiar. So that is the formula for the volume of a sphere. So using integration. So this is another example. Rotation about the x-axis. So if you rotate this one about the x-axis, of course you expect that the same will form the other side, but also in 3 dimensions. So like that, something like that. So you can find using the limits that have been given and the equation, you're able to find the volume. How? Remember, our volume is given as pi, the integral of the limits. Here we've got 1 and negative 1, and then of course y squared, rotation about the x-axis. Since it's easier for okay, so if you have got y squared, it's just going to be x squared minus 1 squared. So in such a case, all you just have to do, I think, if this side is easy to expand, I think that's a better off decision by expanding that. So if you do expand, x squared times x squared will be x squared to the power 4, and then minus 2x squared plus 1. I think that's a better off decision than trying to deal with it as though it's a bigger power. Okay, so we can easily even integrate that. So and then if we integrate that, we're going to have x to the power 5 over 5 minus 2x to the power 3 over 3 plus x, and then of course the limits 1 and negative 1 respectively. Okay, so at that point, plug in the values. Shouldn't be a struggle. So for the first part, for the upper limit, you plug in ones, so you're just going to have like 1 over 5 minus 2 over 3 plus a 1, and then minus the other part. For the other part, you plug in a negative 1. So where you've got the odd powers, the signs will change. So we just have odd powers, so it's going to be negative 1 over 5 plus 2 over 3, and then minus a 1. Okay, multiplied by the pi that is outside. So if you do that, you're going to get 16 pi over 5, 15. Now, just like we had rotation about the y-axis, what you might expect is this shape will appear on the other side. Okay, so so this is something like this. If you have a curve there and then you rotate it, it will also appear the other side like that. And then in terms of 3D, it will be something like that. and then like that. So you can find the volume as well. Now here we'll do the opposite of what we're doing for about the x-axis. So here it's going to be the volume of a solid formed will be the pi, and then the integral of, look at the limits that you're interested in, let's say b and a. So those limits will be on the y-axis as expected, and then obviously it will now say x squared. So meaning that for every equation you have to make x a subject. Yeah, so that means in this case where you have your y being equal to that, you would have to say y is equal to 1 over 3 x. So if you make x a subject, that means you have to multiply both sides by 3. 3y is equal to x, and then of course you can now square x. So if you square both sides, x squared becomes 9y squared, and then you know now what to do. At that point you've got your pi, and then you need to integrate. Okay, you need to integrate what? 9y squared in respect to y. So dy, so of course the power will increase by 1, becomes 3 divided by 3. Okay, and then the integral goes away, and then of course the limit b and a will be applied. So yeah, pretty much what should remain is your volume is pi, and then inside there 9 divided by 3 will just be like a 3, so you have 3y to the power 3, and then the limits, if you have got let's take the limit to be what, maybe 3 and 2. So you just have to plug in 3 and 2 and then subtract. What you get is a volume formed of that solid when rotation occurs about the y-axis.